Good day, Dr. Sulaiman Ibrahim. My name is Oisichin with matrix number 293600. I'm a student from Bachelor of Science with Honours Decision Science, taking a program called SQQM 2033 Intermediate Calculus, and I'm from Group A. Today, I'm going to introduce a subtopic in our syllabus Chapter 2, the application of partial derivative. The partial derivative is used in vector calculus and differential geometry. In mathematics, sometimes the function depends on two or more variables. Here, the derivative converts into the partial derivative since the function depends on several variables. In this video, we will learn about the definition of partial derivatives with an examples of applications of partial derivatives. First and foremost, what are partial derivatives? Suppose we have a function fxy which depends on two variables x and y, where x and y are independent of each other. Then we say that the function f partially depends on x and y. Now, if we calculate the derivative of f, then that derivative is known as partial derivative of f. If we differentiate the function with respect to x, then take y as a constant. If we differentiate f with respect to y, then take x as a constant. One of the applications of partial derivatives is to find the relative minimums and maximums. The definition of relative extrema for functions of two variables is identical to that for functions of one variable. We just need to remember now we are working with functions of two variables. So, for the sake of completeness, here is the definition of relative minimums and relative maximums for functions of two variables. Definition: a function fxy has a relative minimum at the point AB if fxy is bigger or equal than fab for all points xy in some region around AB. A function fxy has a relative maximum in the point AB if fxy is smaller or equal than fab for all points xy in some region around AB. Next, we need to extend the idea of critical points up to functions of two variables. Recall that a critical point of the function fx was a number x equals to c, so that either f prime c equals to 0 or f prime c doesn't exist. We have a similar definition for critical points of function of two variables. Let's continue to discuss this topic with an example to have a clear understanding. Example 1. Find and classify all the critical points of fxy equals to 4 plus x cubed plus y cubed minus 3xy. We first need all the first order to find the critical points and second order to classify the critical points, partial derivatives, so let's got this. Differentiate f with respect to x equals to 3x squared minus 3y. Differentiate f with respect to y equals to 3y squared minus 3x. Differentiate fx with respect to x equals to 6x. Differentiate fy with respect to y equals to 6y. Differentiate fx with respect to y equals to negative 3. Let's first find the critical points. Critical points will be solution to the system of equations, which is let differentiate f with respect to x and differentiate f with respect to y equals to 0. Differentiate f with respect to x equals to 3x squared minus 3y equals to 0. Differentiate f with respect to y equals to 3y squared minus 3x equals to 0. This is a nonlinear system of equations, and this can, on occasion, be difficult to solve. However, in this case, it's not too bad. We can solve the first equation for y as follows. 3x squared minus 3y equals to 0, which is y equals to x squared. Substitute this into the second equation gives 3x squared minus 3x equals to 3x x cubed minus 1 equals to 0. From this, we can see that we must have x equals to 0 or x equals to 1. Now, use the fact that y equals to x squared to get the critical points. When x equals to 0, y equals to 0 squared, which is 0, and we get the critical point 0, 0. When x equals to 1, y equals to 1 squared, which is 1, and we get another critical point, which is 1, 1. So we get 2 critical points. All we need to do now is classify them. To do this, we need D. Here is the general formula for D. dxy equals to differentiate fx with respect to x, xy, times differentiate fy with respect to y, xy, minus differentiate fx with respect to y, xy squared, which is 6x multiply 6y minus negative 3 squared. And we get the final answer is 36xy minus 9. To classify the critical points, all that we need to do is substitute in the critical points and use the fact above to classify them. When a critical point is 0, 0, D equals to D 0, 0, which is negative 9, and it is less than 0. So, for 0, 0, D is negative, and so this must be a saddle point. When a critical point is 1, 1, D equals to D 1, 1, which is 36 minus 9, and we get the answer 27, which is bigger than 0. For 1, 1, D is positive, and differentiate fx with respect to x is positive, and so we must have a relative minimum. I hope that after this video you must understand what partial derivatives is. The easiest way to understand this is a function with multiple variables, where we differentiate the function with respect to one of the variables, regarded other variables are constants. We are coming to the end of my sharing. Thank you for watching.